Hello, my name is Payam Nikhil. It's a virtual presentation of my ICRA 2021 paper called LBGP Learning-Based Goal Planning for Autonomous Following in Front. In this paper, we work on the problem of following a user while staying ahead of them. This task can be challenging as we need to first predict the human trajectory, then find a feasible way to navigate the robot ahead of the human while maintaining a safe distance. Despite several useful applications for autonomous push carts, this problem has received much less attention than the easier problem of following from behind. To follow a user from behind, you can simply use a PID controller to keep a person at the center and a separate PID controller to maintain person-robot distance. In contrast, for following in front, the robot needs to explicitly or implicitly predict the future trajectory of the person and navigates there while maintaining a safe distance. There are many applications that following front can fit in. For instance, if one designs a guide dog robot, it is only useful if it placed in front of the person. Or for an autonomous suitcase application, following front can avoid thefts from stealing the suitcase. In our latest front following work, we presented an extended Kalman filter approach. In that work, EKF predicts position of the person, then a human motion model corrects this estimate by considering the obstacles and a linear motion for the human. To the best of our knowledge, this system was the state of the art for the staying in front task for an unmanned ground vehicle. The contribution of our paper are the following. We demonstrate that the policy trained using our method can directly transfer to the real world without any retraining. We improve the safety and generalizability of our system by combining a robotics trajectory planner and deep RL. Using curriculum learning, we reduce the training time while improving the final return. And lastly, by evaluating our system in simulation using ClearPath Jackal and in real world using Turtlebot 2 robots, we show that our system can be more reliable and efficient for front following in compared to the current state of the art or an end-to-end method. Our learn-based goal planner approach uses the combination of deep RL and classical trajectory planners. Our policy employs an implementation of D4PG to output a short navigational goal. We combine it with a curriculum to reduce training time while achieving a higher return. Then a classical trajectory planner navigates the robot toward the goal. The observation of our network is a stack of robot and human relative states during the last 10 frames with a frequency of 5 frames per second. These observations include relative human-robot position and linear and angular velocities of human and robot. The policy network outputs a short navigational goal relative to the person. We define the reward based on human-robot orientation, alpha, and human-robot distance. The robot will receive the maximum reward +1 if it is in front of the human and doing the front following, and it will get negative reward if it is far away or behind the human. To improve learning efficiency, we employ curriculum learning to train the agent in a series of tasks with increasing difficulty. These tasks are defined based on human trajectory. We start with a straight line and move to more difficult trajectories as we go further in the training. These trajectories include circles with different radius, random curves, and finally annotated paths that are similar to the human movements. We compare our method in both simulation and real world using two baselines. The first one is the latest handcrafted following in front paper, which exploits EKF to predict the position of the user, then using a trajectory planner robot navigate to the predicted position. The second baseline is an end-to-end learning approach. We use the same D4PG implementation with our curriculum learning, but instead of a navigational goal, the policy directly outputs robot linear and angular velocities. The first baseline can compare LBGP with the latest classical robotic method and show how we can improve those results. While the second baseline compare the proposed architecture versus an end-to-end method and show increase in both accuracy and generalizability of our method in compared to an end-to-end approach. We conduct 3 experiments in simulation with different human trajectories. In each experiment, we report the mean person-robot angle, the mean robot-user distance, and the episode accumulated reward. The result for all the simulation experiments using our system LBGP versus baseline are shown on the table. For all the challenging trajectories, our method achieves the highest return. This image shows the trajectory of human and robot during the third simulation experiment using our system versus the 2 baseline. The first row is our system, second row is the end-to-end baseline, and last one is the EKF baseline. If you look closely, specifically in the experiment 2 and 3, the robot is following so similar to the future position of the person. While if you look at the other 2, it is far away in compared to our method. In the following, I will go over the result of real-world experiment. In real-world experiment, we use a Turtlebot 2 robot, while in simulation, we use the Jackal robot. The first experiment is a straight trajectory. For each experiment, we have 4 different initial conditions. In this experiment, in case 2, where robot is exactly in front of human, HC can perform better, which is due to simplicity of the task. It is expected that EKF can solve it optimally. For all other cases, LBGP achieves the highest return. It is interesting to point out that while in simulation, end-to-end method work to some extent, but in real world, it is completely failed. It may mean that the end-to-end method may be suitable to learn a model for a specific robot, but it is not generalizable to other cases and will overfit to that specific robot in the simulation. As the end-to-end method failed most of the experiment by colliding with the user or getting too far away, we are not including those videos. Here you can see the video of our method during the straight trajectory experiment with 4 initial conditions. This slide can show the performance of HC baseline for a straight trajectory. And as you can see, for instance, for the behind initial condition, even the robot cannot get in front of the human at the end. This is a result of S-shaped trajectory. Again, our method achieves a much higher return. This time, you can see a larger difference between HC and our method. As for S-shaped trajectory, LBGP can implicitly predict the future trajectory of the human and get a better performance. In this video, you can see the performance of our method for all the 4 different initial settings during the S-shaped trajectory. And as you can see, for all of them, it has a good performance of following in front. And here you can see the performance of HC baseline for the same experiment. As you can see a much worse performance in compared to LBGP. And this is the last experiment, which is a U-turn trajectory. And again, with a higher margin, our method achieves the highest performance. The last task is much harder, and this time the person will perform a sharp turn. So any error in prediction can keep the robot behind. And that is why we have a much higher margin. Here we have the performance of our method during the last experiment. And this is the same experiment for HC baseline. To conclude, We propose a hybrid follow-ahead system. We address the limitation of the end-to-end and classical robotics methods by combining deep RL and a trajectory planner. Our results show that our system can outperform previous work in an obstacle-free environment. Using a planner, we improve the generalizability and safety of the terrain policy compared to an end-to-end method. This allows us to successfully perform zero-shot sim-to-real transfer. Thank you for attending this virtual presentation. Please scan this QR code to get more information about this paper.